we're going to explore actually this unit, right? We're going to explore how atoms are structured and how ions form, how the periodic table are organized, and how we use chemical formulas to represent both ionic and molecular compounds. By the end of this lesson, you will understand how the smallest particles of matter connected to the big ideas of chemical behavior. So let's get started. So at the unit 2 and the previous chapter, like in the chapter 2, unit 2, we'll finish talking about the atoms, how they discovered the atom, and we talk about Rutherford and his experiment with the gold foil. Remember that, right? That experiment showed us that atoms are mostly empty space and with a tiny and heavy, dense nucleus of the center. If an atom were a size of a football stadium, so the nucleus would be here in the center, exactly like the size of a blueberry. This is how small and dense the nucleus are. So we saw as well that later James Chadwick discovered the neutron. So the neutron are, while the protons has a positive charge, the neutrons has no charge at all. And that completed how our modern picture of the atoms. So this discovery helped us to understand why atoms behave the way they do. So since we talked about the protons, neutrons, and electrons, which are the main subparticles that form the atoms, I know that they already discovered the quark, for example, right? The quark particle. However, we're going to remain talking about the main subparticles, which is electrons, protons, and neutrons. So here is this table is only to show you, and I want that you pay attention on the mass of those three. So electron has a very small mass compared to the others, and the charge of electron and protons are equal, but with a different sign, so they're opposite sign. So while the electron is -1, a proton is +1. And that is a way to identify the atom, right? If I want to talk about just one single atom, of course this is not an atom, this is just a way to represent. So I need something to represent. And the way to represent is by the number of protons. And that is the atomic number that you're going to see in your periodic table. If you want to talk about that, like the only thing that you really need to know is like proton will never change. The neutron can change, the electron can change, but the proton is the density of the atom here. Okay, so if I could use ID for the element, so I would use like this. ID number for hydrogen would be 1. Okay, so because they have 1 proton, that is the identity of the hydrogen, so will not change. Okay, that. And also the atom has a mass, and the mass is the mass of the nucleus. So proton plus neutron. And probably you're asking me why you don't add the electron. We don't add the electron because, as you saw in the previous slide, we have a very small mass. So it's just one of these. So now you know that why we don't use the electron. So it's kind of, if you go to weigh yourself before your shower, so you go to the balance and they're like you have nothing on your body, like just your body, and go there, and it was like, oh, I will take out my ring. So that doesn't make sense, right? Because they will not change your weight at all, because this is so light. This is how electron will affect the weight. This is why the mass that we represent by A is the sum of protons plus neutrons. So, and also we use symbols to represent the element, like C for carbon or O for oxygen. But also you need to pay attention because some of the elements, the name come from different languages, like a Greek word, like for example, mercury. Mercury, you use the Hg. So that is the symbol. Why? Because it's coming from a Greek word, hydrogen. Sorry. That means liquid silver or water silver. That's Greek. And this is why we use Hg. Like silver, we use Ag. So some symbols will have a difference, like the initials from the name, because they come from a different language. So this is why it's so important to take your periodic table and read, like just to get used with some symbols. So another very important thing is only the first letter of chemical symbol is capitalized, like here, and mercury. So here are some of the other elements, common elements like chromium, chlorine, carbon. Those are very simple, and the symbols are very easy to find because it's come from the name: cobalt, CO, copper. Here is CO. If you use CO, it will be cobalt. So pay attention and the symbols. That will make your life easier if you get a use of those, or you need to look for some element in the periodic table. And we have isotopes. What is that? Isotope is when it's the same elements with a different number of neutrons. That we call isotopes. For example, magnesium. Here we have 3 naturally occurring isotopes: magnesium 24, magnesium 25, and magnesium 26. So what is changed over here is only the number of neutrons. The number of protons are the same because that is the density of magnesium. So the way to represent that, first before we talk about this, is we represent the symbol like this. So we have the symbol, the chemical symbol of the element. The mass number we're gonna be in the right, the left side, and the up side, and down here in the left side with the atomic number. To represent isotope, we normally use the chemical symbol or the name of the element, dash, and the mass number of the isotope, like neon 20. Okay, so here you can see in this table that the only thing, this is why I brought this table for you, is to show you that the protons are not changing over here. What is changing is the number of neutrons. Okay, so this is why the mass is different. Another different thing here is the natural abundance. The natural abundance is how easy it's to find those in nature. So 90.48% of neon that we're gonna find in nature is neon 20. And this is why if you go to the periodic table, you're gonna find the mass for the neon 20.1 something. It's not a whole number, because we need to take in consideration also the mass and the abundance for the other isotopes, and then we add together. We're gonna do this later. Here at the isotope for hydrogen, we have the protium, deuterium, and tritium. So the only thing that is changing here is the number of neutrons. If you see, the number of protons are the same for all. So we have 1 proton for each of those hydrogens over here. But what has changed is the number of neutrons, and of course the number of mass, the mass number. So atomic mass unit. This AMU means atomic mass unit. Okay, and here is the percentage that is changed. So the hydrogen that we use a lot even to form the water is this one. And there's 99.989% of the hydrogen that we're gonna find in nature is this one. Okay, deuterium normally we represent by D. So if you look at a book in the library and it was reading chemistry, of course the best thing in the world is those chemistry book. And oh, sorry, let me get back. Even this is against. Oh, okay. So here, so I was trying to write down. So you're gonna find this D2O. So that is isotope of hydrogen. This is deuterium, and are very used in the nuclear industry, also some equipments that we use because they don't interact with our samples, so we use heavy water. This is how we call that D2O. And we use special equipment, the mass spectrometer, to find out the abundance and the elements that we have. So the current and natural abundance of isotopes can be experimentally determined using an instrument called a mass spectrometer. So the sample here, so we have the enter of the sample here. We use a very small quantity of a sample. So then this sample is vaporized and exposed to a high energy electron beam that causes the sample atoms or molecule to become electrically charged, typically by losing one or more electrons. And then we can find the different types, the different isotopes, and through this equipment. So let's try to check your knowledge over here. See over here, this is image that I got from the FAT Colorado. So this is a very good tool, so you can check, so you can play with the atoms over there. They have a different simulations over there. It's really good and it's free to use it. Here in the first example, so all carbon, so the number of protons that you see red dot over here are 6 for all. And if you, let me grab another pen over here. So all 6, see? What is changing over here is the number of neutrons. And the first one, we have C12, this is how we represent, because we have 6 neutrons and 6 protons, so 6 plus 6 is 12. And here I have one more neutron, so this is another isotope, so C13. And here we have 2 more, so C14. All those are neutral elements because they all have 6 electrons, see? 6 protons and 6 electrons. When you have the same quantity of protons and electrons, we have a neutral element. But if you have more electrons, like in this case over here, we have a 6 proton because this will never change, but we have 2 more electrons. So we have an ion over here, so that means receive electrons for someone else, okay? So I think this is what you need to pay attention. Protons will never change. What changes in the isotopes are the number of neutrons, okay? Atomic mass. Each proton and each neutron has a mass of 1 atomic mass unit, and we add all together. However, most elements, as we talked about before, exist as a mixture of 2 or more isotopes. So we need to take in consideration that. How we're going to do this is using the abundance. For example, here is 90.40% with atomic mass of 20. That is the fractional abundance over here. And they have a 0.27% of 21 and 9.25% of 22. How that works is in the paper. Let's practice it together over here. So here is an example. So an element has 2 naturally occurring isotopes. Isotope 1 has a mass of 120.9038 atomic mass unit and a relative abundance of 54.70%. And isotope 2 has a mass of 122.9042 atomic mass unit. Find the atomic mass unit. So the atomic mass of this element, identify it. First thing is, look at this, and it's like, oh, it's missing here the percentage of the second one. Okay, but the problem says that it's only 2 naturally occurring isotopes. So 100 minus 54.7 will give me another one, right? So, oh, let me grab another pen over here. So if you use 100, because that will be 100% of those, minus 54.7 will give me the other percentage, right? So we're gonna have how much? 5.3, and then will be 45, right? 45.3, because you have 45.3 we're gonna have our percentage of your second isotope. So the average mass will be the percentage divided by 100. You cannot use directly the percentage. You need to divide by 100. So then multiply by the mass, which is over here. And then we're going to add with the product of the percentage, which is the abundance of the element, the second isotope, times the mass. And then you're going to find the average atomic mass unit. And if you have the periodic table in your hand, you're going to find who is this element. So this is the antimony over here. See the symbol? So you need to be aware that if you're not use it with the periodic table, you're gonna waste time looking for the elements. So another example, my suggestion here is stop the video and try by yourself. So in this case, we're gonna do the same thing. So we have the abundance and the mass, atomic mass unit, and the same with the chlorine 37. So we add all together and we're gonna have 35.45 atomic mass unit. Don't forget the unit. Remember what I talk about the unit. It's very important. We don't accept the negative numbers over here. So atomic notation, I already explained a little bit behind, like in the few slides ago. So we have the atomic number that will appear here and left side. This is the symbol of the element. Only the first letter is caps letter. So we have the mass, and then we're gonna have the atomic number over here. So that is the representation, and probably gonna find one of the questions like this in a lot of exercise. So you need to know the mass is on the top and the left side. Atomic number is down there, and the bottom and the left side. Okay. So in here, normally we have the charge, if you have a charge. Okay, so let's practice. So here we have an element, so just remember that we have atomic mass, atomic number, sorry, and the number of mass. So here I have this cadmium over here. So we have the mass and we have the atomic number. So the atomic number is the same number of protons. So I know the atomic number will be that. But mass and neutrons, so if I have the mass and I have, the mass is proton plus neutron. So if I have the mass and I have the protons, I can find the neutrons. That will be mass minus protons, right? So we're going to do that, so 47. And electrons, it's a neutral element, so I don't see any charge over here, so it will be the same number of protons. And I have the atomic number and the mass number. So here I have a charge. So if it's positive, so that means this element lost 3 electrons. This Y is more positive. So it's like if you have a graphic. So the protons and neutrons, electrons, must be the same if you have a neutral element. But if you have more protons than electrons, that means you lost electrons here, so electrons and protons. So we have more positive charge, see? That's why positive means that you lost some electrons. And if you have here more electrons, so it got more, this element got more electrons from somewhere, and so it will be more negative because electrons are negative. So positive means lost electrons. So when you calculate electrons, you need to take in consideration, so this is 28, right? And so protons, so electrons will be this minus 3, so it will be 10. Neutrons will be mass minus protons, okay? So I went to periodic table to find the mass, which is 28. Actually, sorry. I went to periodic table to find the atomic number, which is 13. Okay, that's for aluminum. So mass is over here, 28. Good? So the same thing for this one, but this has a charge of -2. So -2, that means gain electrons. This is why it's negative. Gain more electrons than protons, so we have more negative. This is why negative charge shows that you gain electrons. So that you need to add 2 more electrons to the number of protons, so it will be 10. So we have the atomic number and we have the mass, which is 70. Okay? So we're going to talk about ions better in the next slides. But first, let's go over to periodic table. So imagine if you don't have the periodic table, everything completely disorganized. Would be a crazy, would be a really crazy world. It's like if you go to your wardrobe and all your clothes are a mess. You cannot find anything, a shirt, underwear, anything. And that gives you a headache, right? It's horrible. So the thing that you need to do is organize so you can find easily where you're going to find underwear, shirts, pants, everything. The same thing with the periodic table. So we have different elements, like more than 90 elements. So it's so big number of elements. The natural accords plus the one developed by man. So the periodic table came to help us with that. And of course, there were a lot of scientists working with the periodic table, a group of scientists. But the most important one that I think, because I have a picture with him, is Mendeleev. Mendeleev is not because he created vodka. No, it is because he was very smart. And I will tell you a little story about him. So independently, he organized that they are separate, okay? So the scientists are not working together. They're in different part study. Like Mendeleev and Mayer was in Germany, and Mendeleev was in Russia. So they start organizing the elements by themselves, like, trying to find a periodic relationship. So among the properties of the elements known at the time. And for example, lithium over here, sodium, potassium are all shine, conduct heat and electricity well, and have similar chemical properties. So, okay, we should put all those together, right? Calcium, strontium, barium are also shine, conduct heat, electricity, but are less reactive than those over here. So this is how they start organized. Both Mendeleev and Mayer published tables with the elements arranged according to increasing atomic mass in that time. Okay, but Mendeleev left some empty spaces, like you can see over here. But he predicted the properties of those elements that actually was discovered after years. So he used his table to predict the existence of elements that would have the properties similar to aluminum, silicon, but were not yet known. So the discovery of gallium in I think 1875, and germanium was 1886. Yes, that provided great support to Mendeleev's work, and this is why Mendeleev, everybody talk about Mendeleev, because he left empty space, and he said this is the property of those elements that we don't know yet. But this element, if you found, will be these characteristics, and they found that. So and that support his idea and his work, his science. This is how important is Mendeleev. Okay. So the modern periodic table, of course, everybody, a lot of scientists work in the periodic table, and it became more apparently more visible, more easy to understand, right? And now involve the atomic number. So we have the periodic law. So the properties of the elements are periodic function of their atomic number. Remember, we started the atomic mass, now use the atomic number, the mass, And today we use atomic numbers. Of course, the mass also increase, right? A modern periodic table arranged in the periods and groups. So periods would be the horizontal rows, right? So if you go to your periodic table over here, so we're gonna have a periodic table over here. So we're gonna have the rows over here. So we have a number 1, 2, 3, 4, 5, 6, 7. So and then we have that is the periods, and the groups are in the verticals. So that is the groups, number 1 to 18. But the old periodic tables, you're gonna see like a 1A, 2A, that the main elements goes up to 8A was 1A, the main elements to 8A, and the middle, this part over here, was B. So we start now. Normally, the new periodic tables come in 1 to 18. So valence electrons. So the valence electrons are the electrons located in the outmost shell of the atom. So the elements, the electrons, the valence electrons of metals is 1, 2, 3. The valence electrons of non-metals 4, 5, 6, and 7. How we do that? So valence electrons, like here. Let's go to sodium. Sodium, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they have one more shell that is only 1 electron. This is the last shell. So the last shell does carry 1 electron. So the outmost electrons in the element here is 1, and all the elements over here in the first group has just 1 valence electrons. Okay, so these are the electrons that are used to bond, or the atom can give away, or the atom can negotiate that, so they can share, so that outmost electrons. So we know that in the nucleus we have protons, right? And the electrons are around with negative charge. So the attraction between the protons and the electrons close to the nucleus are stronger. So it's hard to move or take out those electrons. But as you get far away from the nucleus, the electrons are more energetic because they can move better, and it's easy to remove those electrons because they are far away from the electrons. The proton, so that is the outmost shell over here. And all the first group, this is fantastic, but all the first group elements has just 1 electron in the outmost shell. When you go to the second, so we have a 2, so that is 2 valence electrons over here, because all the elements over here, so magnesium, if you keep it going over here, magnesium can have a 2 in the last shell, so that will be 2 electrons the outmost shell, and all those elements will have the same, so that is 2 valence electrons. And over here, group 17, so I know that is hydrogen should not be here, so we brought just to show you that is not a metal. This is no metal, okay? And here we have group 17, so all those elements here, fluorine, chlorine, bromine, iodine, all has 7 valence electrons. And see the group 7? So that is the number of valence electrons. 6 valence electrons, 5 valence electrons, okay? So this is the periodic table. So you're going to find the chemical symbol, you're going to find the atomic number, mass numbers. Some periodic tables give you the state of the element, okay, in the standard temperature. Some other will give electron configuration as well. So it depends of the periodic table like this, give you which one is solid, which was liquid or gas. See, we have a liquid, we have solids over here, and we have the red gas. And Some will tells you what is the metals by color, and no metals and metalloids. So we have metalloids over here, we have metals, all these colors over here, and they have no metal in green over here. Okay, so and we have the classifications like metal, non-metal, and metalloids. So that is the main groups that we're gonna have. It's 1, 2. This is the groups that we're gonna main groups, because we it's easy to find the properties. They have fixed charge. So this is 1 and 2, and then goes to 16, 18, 17, 16, 15, 14, 13, all these groups over here. Okay, so that is the main groups. So we have transitional metals, 13 to 12 over here. These are the transitional metals. And we have inner transition metals. So the row of bottom on the periodic table. So we have lanthanides and actinides over here. Okay. Other main families or groups over here: alkali metals, earth alkali metals, alkaline earth metals, and we have the halogens, noble gas, and the other groups. We're going to talk more about those 5 over here. So alkaline metals are very reactive. Remember that I said they only have 1 electron. So lithium, we're going to have just one electron over there. So we're going to have sodium, just 1 electron in the last shell. We have potassium, just 1 electron in the last shell. So all those, if they lose that electron, they'll be so stable. So they are very reactive. And even here is the sodium. So just a little piece of the sodium in water. See how far you can see fire. It's an explosive reaction, actually. So we do this, and it's secured, like taking care of the safety, because it's explosive, and it's just 1 small piece. This is how explosive it is. So lithium, sodium, potassium, they are all alkali metal, very reactive. Okay, so alkaline earth metals, they are very reactive as well, but not as much as the alkaline, which is the group 1. This is group 2. All those elements has only 2 valence electrons in the last shell. So like magnesium, calcium, they have 2 valence electrons, and they also need to lose those electrons to be stable. So they are reactive, as you can see over here in the photo. They reacted, so we have some bubbles, you have some fume over there, but you don't see fire, you don't see any explosion. So they are very reactive, but they are not as reactive as the first group. So non-metals, mainly if you're gonna talk about the groups, we have the non-metals over here in red. See, that is the non-metals. They are 5 of those are solids in room temperature, like carbon, phosphorus, sulfur, selenium, and iodine. 1 is liquid, which is the bromine, and the 11 are gas, like hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, or so on. Non-metals tend to be poor conductor of heat, electricity, not ductile or not malleable, so they break down easily, like sulfur, all those elements. They don't fold like metals. Gain electrons when they undergo chemical reactions, so they tend to gain electrons, like oxygen, carbon, sulfur, bromine, iodine are non-metals. So halogens is very important elements. We use a lot of, you're going to find a lot of products with the halogens, like hydrochloric acid, or some are used in health, like fluorine. They are always found in nature as a salt, like chlorine, a greenish yellow gas with a pungent odor. Bromine, a red-brown liquid that easily evaporates in a gas. We have iodine. It's a very purple solid, and very volatile. You could be here. Fluorine, a pale yellow gas. Okay, so this is the main characteristics of that. And noble gas, they are very stable. So they don't tend to react. So this is why you call noble gas. And we use, for example, in balloons like helium. And why you use? Because it's safe to use, because it's a noble gas, will not react with anything, okay, with the other elements. Neon we use normally in electronic signs like argon, so small components of our atmosphere. So we have krypton, xenon, all very stable elements. So let's classify here which one is metal, non-metal, and metalloids. Metalloids are elements that let's get back over here in this. So that is the metalloids, or also called semi-metals. So we're going to see 1, 2, 3, 4, 5, 6, 7 elements over here. So they are, they have characteristics of metals and also non-metals. So some depend on the conditions of those. So let's start with these elements over here and tell me which one is metal, which one is non-metal. Let's start with the lithium. That is a metal, right? OS, I will not tell you who is OS. I will ask you to grab your periodic table and tell me what element is this, and is this a metal or non-metal? If you're looking for your periodic table, you're going to find the period 6 and the group 8. That is osmium. That is a metal. So we have a hydrogen, which is a non-metal, and we have germanium, which is metalloid. Okay? So an element that is liquid at a room temperature and conduct electricity. So that is metal, and it's mercury, right? So an element that is solid at room temperature and is a poor conductor of heat, non-metal. Okay? So let's see those questions regarding nitrogen and antimony over here. So here it says that are both non-metals. Is that right? Wrong. Nitrogen is a non-metal, but antimony is a metal. Actually, a metalloid. So they are in the same group. Yes, they are, and they are in the group 7. Actually, group 15. So nitrogen and the antimony are in the same group, group 15. Okay, I was looking to the atomic number of nitrogen, sorry. They are in the same period. No, they are not. While nitrogen is the period 2, antimony is in the period 5. They are the same state. Also false. Okay? So let's go to family name. This is why it's really important to study and watch my class with the periodic table in your hand. So what is that Mg? That is magnesium, and is in the alkaline or metal, right? So number, so I have in the group 2. So the old periodic table is 2A and the new periodic table is 2. And is in the period 3. And the valence electrons, if in the group 2, has 2 valence electrons. Let's go to gallium. Who is gallium over here? It's a boron family, so it's a group 13. And the period of gallium is 4. And the valence electrons is 3. Has 3 valence electrons in group 13. So we can predict the ion charge. So the periodic table can serve as a guide for predicting the ionic charge of main group elements. Many main groups metals lose electrons. Okay, so let's go to group 1 and 2. So, let me erase that because this is group 1 and 2. So group 1 and 2, you're going to see +1 for the group 1 and +2 for the group 2. They tend to lose electrons. Remember when I draw the valence electrons for you? So we saw the group 1 and group 2. So 1 valence electrons, 2 valence electrons. So that is the electrons they can lose over here. No metals, the main no metals, gain enough electrons to give them the same number of electrons as an atom of the next noble gas. So group 17, they will gain 1 electron to be with the 8 electrons in the final, the outmost shell. So that will be equal to a noble gas. They'll be stable. It's like us. We always look for stability, right? So in the group 16, they will have 2. So -1, -2. Okay? So what is the charge? So neutral atoms has no charge at all. Okay? So they must contain number of positive and negative charge in the same quantity. The same quantity. So the number of protons must be equal to the number of electrons. Remember the small graphic that I wrote for you? So positive and negative. So if they have the same numbers, they are neutral. Therefore, the atomic number also indicates the number of electrons in a neutral element. Ions is when they have a difference, when they lost or gain electrons. So if I have lost electrons, so now I have more positive, so I be a cation because I'm positive, right? If I gain electrons, so I will have more electrons than protons, so it will be an ion, which is negative charge. And this is when you gain electrons, you have a negative charge, and you lose electrons, you're positive charge. So let's understand better this difference over here. Charge, so neutral elements equal protons and electrons. If I have an ion, so let's put the graphic over here. See, I draw the graphic for you just to see it. So protons and neutrons are the same. This is protons and the electrons, and the electrons. Protons and electrons. Now I have more protons, so I have cations, it's more positive. And here I have more electrons, it's negative. Okay? So how they form ions? Losing or gain electrons. Okay? So this is how they do. So atoms that gain 1 or more electrons will exhibit a negative charge, and it's called an ion. For example, a neutral oxygen atom has 8 electrons, and if it gains 2, it will become an ion, -2. So an atom that loses 1 or more electrons will exhibit a positive charge, and it's called a cation. So a neutral sodium has 11 electrons. If this atom lose electron, like lose 1, so we're going to have 1 charge, +1. Okay? So as I said, in periodic table we can predict it, and I showed you how you predicted the charges, right? So I showed you how to predict the valence electrons, and I'm showing here how to predict the charge. So group 1 and 2 is always +1 and +2. Okay? If you go to the main groups and the non-metals, so we have here this group in yellow, so it will be 3+, and we're gonna have non-metals, so we're gonna have here charge -1, -2, -3, -4, right? So we can gain electrons. Okay, so we have some elements that are fixed charge, like here zinc, cadmium +2, all those elements here +3, or the negative charge over here in the group 17, 16, 15, 14, and the group 1 and 2, they are fixed charge. However, some elements has different charge, like iron. Iron can have charge 2 or 3, for example, +2 and +3. So, and that is how we're going to know, by the name or by the formula. So let's go to the chemical formulas. So molecular formula indicate the composition of a molecule, so of compound, and giving the actual number of atoms of each element in a molecule of the compound. For example, if I have CO2, I have 1 carbon, 2 oxygen, so carbon dioxide. So as that subscript here indicate the number of each type of atom. So if I do this, I know that it has 2 hydrogen and 1 oxygen, right? So this, you know, that is the water molecule. I can do this. I have 2 water molecules. But I cannot do this to show that I have 2 water molecules because they'll be different. Remember this, right? We learned this in previous slides. Okay, so this, imagine if I tells you, okay, so this is water. You gonna drink this? No, right? Because you know this is not water, right? Okay, so structure formula is this. So we display the structure of the molecule. Here I have benzene, so I have 6 carbon in a ring, see, the cycle, and 6 hydrogen. And here we have the ball and stick model. So the 3-dimensional ones, space filling model, like here. So show the same information as a molecular formula, but also show how the atoms are connected. Here I can tell you that is a tetrahedral geometry and thus methane. And I have 4 hydrogen and 1 carbon, right? So there are different ways to show how the atoms are connected. Molecular and ionic compounds. So when the 2 or more elements combine to form a compound, an entirely new substance results. So if I have a carbon and the oxygen, I can produce CO2, I can produce CO, so it will be different compounds, right? In ordinary chemical reactions, the nucleus of each atom and thus the identity of element remains unchanged. So that means the number of protons will be the same. So if I have a carbon as a product, I also has a carbon and a reactant. They will not change the number of protons to change the final product. What is changed is the combination of the atoms. So a carbon can connect with the 1 oxygen forming CO, for example. I could have a CO2, or I could have just 1 carbon with 1 oxygen. So it's the way they combine, is the way they are bond with the other elements, okay? So electrons participate in chemical reactions by being gained, lost, or share electrons. I will ask you to watch this small video over here later. So molecular compounds, they share electrons. They don't give away. It's like here, if I go to, let me, looking for my pen again, here, no, this. So why I cannot use my pen? Okay. Oh, I think I'm gonna use it. Okay. So chlorine has 17 electrons, okay, and 7 valence electrons. That means, taking into consideration that all the elements wanna be like noble gas, which has 8 valence electrons, okay. So all those elements trying to connect or bond to be stable like noble gas. We call the octet rule. So chlorine has 7 valence electrons. So only need 1 more to be stable. So even if you're a person and you don't know anything about chemistry, you're gonna look at the chlorine, it's like, okay, this chlorine will not give away. And so they can get together and share this. So now both of chlorine will be happy, right? So I can say that they are happy because they have 1, 2, 3, 4, 5, 6, 7, 8, because one of those they are sharing a pair over here, okay? So in general, nonmetals plus nonmetals form a molecular compound, also known as a covalent compound. So they exist as discrete neutral molecules. So the number that you're going to see is the number of the atoms they have. So normally they exist as gas, liquid, or soft solids. They have low boiling liquid point and low melting solids. Okay? So some elements, like it's not over here hydrogen, but hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, they only exist in nature as a molecule. So you're only going to see A2, N2, like diatomic elements. So see here, 7 make 7. We have 7 elements, including the hydrogen over here. They are diatomic. So you will not write down, if I write down a reaction like this, let me show you here. Let me pen here again. So if I do this, this is wrong because oxygen cannot be by itself, so O2, okay? Should be O2. So it's really important because at some point we will need to write down a reaction and you need to know. So ionic bonds transfer of electrons. See here my little sodium and chlorine. Sodium is giving away. Sodium has 11 electrons and 1 alone electron leaving in an almost shell over here. This is full shell, here inner shell, and here also full. So this is sodium, and this is the one that sodium will give away. And the chlorine has 17 over here, so I have a space just for one more because it has 1, 2, 3, 4, 4, 5, 6. So 6. Okay. 3, 6, 7, 3, 6. Wait, just through here. Okay. 2, just 7. So only need one more. So this will come here and complete this. So they bond together because they form ions. So as soon as sodium give away, form sodium plus, and chlorine will turn chloride because it has a negative charge. So negative and positive attract themselves, so they form a very strong bond over here. So in general happens between metal and non-metal. So electrons transfer from metal atom to non-metal atoms. So metal atoms form positive charge, so positive ions, and non-metals negative ions. So these opposite charge ions attract one another by electrostatic attraction and form ionic bonds. Ions remain together to form an electrically neutral ionic compound. So like here, so I have a plus and plus 1, negative 1. So if you go this summatory, it will be plus 1 minus 1, so which is 0. It's neutral. So forms a three-dimensional array, not a discrete unit. So that is this form, beautiful form, lattice form. So and we write as empirical osmolarity ratio, sodium chloride. So actually the structure of the sodium chloride is like this. We have several sodiums and chlorides, so positive and negative charge together, forming this beautiful and strong structure. But we don't write down like sodium 1000 something and chloride more 1000 something. No, you write down as a simple smallest ratio that I call empirical formula, or unit formula will be sodium and chloride. So ionic compounds, they have a strong bonds, very strong. They held together by powerful electrostatic forces between oppositively charged ions like magnet locked in place. Solid at room temperature. Most ionic compounds are crystalline, solid with a rigid, repeating structure called lattice. This beautiful structure that you see here. So high melting boiling point takes a lot of energy to break those ionic bonds. So they melt and boil at high temperature. They don't conduct electricity if they are in solid form, but they will conduct electricity if they are dissolved in water. Like you see over here, like water or diionized water, you don't conduct electricity, but if you add salt in water, so you're gonna have electricity. If you touch only the salt and the solid form will not connect electricity. The ions must be free in order to conduct electricity. These are called electrolytes. Often soluble in water, like sodium chloride in water, they dissolve in water, especially those with alkali or nitrate ions. But not all. Some are insoluble and form precipitate. Okay? So let's do exercise over here. In every ionic compound, the total number of positive charge of cations equal the total number of negative charge, the anions. Thus, ionic compounds are electrically neutral overall. Using the ion cut out, form a neutral compounds. How that works? So first you need to know that we start a formula with metal and then it goes to no metal. Okay? So let's go to periodic table. So lithium has a charge 1, right? Let me grab my pen over here. Again, I'm losing my pen. So it's +1, +2. And I know this is -1, -2, -3. So let's go. Lithium is over here. So I know that is +1. And I know bromine is -1. If you cross the charge, forget about the sign, just the charge, I have lithium, bromide. Let's go to Mgs. Magnesium, group 2. So it will be Mg +2. And sulfur is -2. So let's cross. And you're going to say like, okay, Mg2S2. But we use unit formula. Unit formula is the smallest formula that you can have. So you can divide both by 2, right? Common factor. So Mgs. And here I have fluorine and strontium. So 2. Oh, sorry. Fluorine is, oh, you're right. I'm sorry. We don't start with fluorine, okay? We start with strontium, which is +2. Fluorine, group 17, -1. Cross the charge. So it will be this. Look at here. So if you have, imagine, I have a 2. We know the charge of this is -1, and I know the charge of this is 2. 2 times -1 is -2. It will be 2 plus -2, which is 0. So this is a neutral compound, okay? And we have selenium, and we have aluminum over here. Selenium is over here in a group 3. Oh, here. See, I have -2. So let me put it over here. Selenium, -2. Aluminum is +3. So if you cross the charge over here, forget about the sign, you're going to have this. Good? So then we go to this one. Look at this. I have a copper 1+ charge and a copper 2+ charge. So we're going to write down copper +1. Nitrogen is -3. So we're going to cross, I will have this. If it's a copper 2, will be copper +2. Nitrogen is -3. So we cross the charge and we're going to have 3 nitrogen 2. So remember, 2 over here is the charge of the copper, 3 over here is the charge of nitrogen. If you multiply 2 times -3, it will be -6. 3 times 2 will be 6. So 6 minus 6 is 0. So neutral compound. Good? You can practice more. Molecular formula indicate kinds and number of atoms present in a molecule. Empirical formula express the simplest or smallest whole number ratio atoms with a molecule. So, ionic compounds are based on the simplest ratio of ions, as you saw before. And we draw some of the compounds that we had 2 and 2, and we divide both by 2 to have the simplest formula. And then look at those and classify as empirical formula and molecular form. So if you go to N2O4, so is that molecular or empirical formula? It's molecular. If I have to write down an empirical formula, I would divide by 2, right, both sides, and I would have NO2, right? NO2, because I'm going to divide this by 2 is 1, this by 2 is 2. This is empirical formula, and that one is molecular formula, but I can reduce that to empirical formula, right? And it would be CH, because I can divide both numbers by 2 as well. Let's practice a little bit more. Look at this atomic representation and tell me which one is ionic and which one is molecular. Yes, you're right. The first one is ionic. It has a lattice structure. Have a bunch of positive and negative charge, but the other one is molecular. So here, was not to show you, but now it's over here. That's okay. So we have a molecular compound. So we have a non-metal plus non-metal. Here, see, this is a metal and this is a non-metal. So that's ionic. And here I have non-metal plus non-metal. So we know that is molecular. And here we have a metal and non-metal. So it's ionic. So we have a metal with non-metal. Oh, I cut from that. Sorry. Metal is the potassium over here, and we have a polyatomic ion over here. Okay? So, let's press a little bit more. Which is the correct chemical formula for the compound formed between phosphorus and calcium? Look at that. We have phosphorus over here and the periodic table, and calcium, so phosphorus and calcium, the second group. You know the calcium, so we know this is wrong because we don't start with non-metal, right? The only thing that you could have a question is those 3 over here. So I have calcium group 2, and I have phosphorus that has a charge. Look at this. -1, -2, -3. So if you cross over here, I'm gonna have calcium 3, phosphorus 2 over here, right? So that is my answer.